Thank you. Okay, now it's working. So I want to really also appreciate some of the other guests outside the country and those within. I really want to appreciate the Vice Chancellor of this great university. At a time like this, I'm told that it's a transitional period. One is excited to be here on campus. I know we had the privilege to move around, but this, what we need to have seen is something to write home about. Bring the greetings from the Obafemi University. In the university, we have 14 faculties, and we are in the Faculty of Science. So this is the building for the Faculty of Science, the entrance. So the Faculty of Science is also under the Yellow House, popularly called the place the Yellow House. So, so the department is housed also under the Faculty of Science. So background information, like I said, one can mean different things with different people, and so we need to be able to have a good definition what we are working on. So I gave the background of what is the definition of a fluid, and I said the fluid is a substance like liquid, gas that continually deforms and flows when subjected to a force. So there will be a shearing force for it to be able to move. But more importantly, it has no fixed shape and takes the form of its container. And we have seawater, you can see it's contained within membrane. We have water in the bottle, takes the shape of the bottle, and so on. So we have this as our basic definition. So also in fluid dynamics, we talk about laminar flow. It's a type of flow in which the fluid travels smoothly, and it's also regular patterns. A very good example of this is when you open the tap in your bedroom, or when you want to wash your hand, when you open the tap gently, you will notice that it's regular, it's smooth, it's glassy, beautiful to look at. But the moment you increase the knob, then it becomes scattered, it becomes irregular. Okay, so that's what we meant by this. So typical example are oil flow through a thin tube, or blood flow through the capillaries, the smoke rising in a straight path. When you're taking a cigarette, you can see the smoke going very smooth, but after a while it scatters, it becomes irregular. Okay, so in contrast, we have what we call the turbulent flow, in which it is irregular. So I've given you an example when you open. So it's irregular, it's fluctuation, it's mixing, and so we need to attack it by taking average. You cannot do it the traditional way. Okay, and then this gives you an example of what is modeling, because this is where the whole bulk of the discussion is all on. So modeling, I put it here as modeling in applied mathematics. We have the real world problem, and it's very big. It's a big problem. It's difficult to conceptualize all the things that comes into play, and so therefore we need to make some reasonable, other fiscally reasonable assumptions that can help us to make the problem trackable and then be able to work around. So if you can simplify the problem as much as possible, then you are here. But so what is germane is to make the assumptions. Okay, and then once you make the assumption, you have a simplified problem, and this simplified problem is put. It's called what you call the mathematical building, mathematical modeling of the problem, and then you have this mathematical model that needs to be attached. You have to find a way to solve it, and to solve it, you have to find a solution. If I can find the solution successfully, then I have the results which I have to interpret, and then I continue in the circle, and then check their assumptions, then I continue in this circle. Change the assumption, and I'll show you examples of how I've navigated in the ocean of water over a period of time. Okay, so next, mathematical model is an idealization. That picture depicts what I want to talk about. So the idealization possesses some of the features of reality, but not all. Okay, thank you. But not all. Okay, such studies are very essential feature of science, technology, engineering, and mathematics. This step, we're all familiar with this. Okay, so background information. What are the equations that describe the laminar flow? For us to be able to describe successfully what the laminar flow is, we need to have what we call the conservation of mass. That is not destroyed. Okay, we have conservation of momentum. We also have conservation of energy. We are talking of conservation of energy. We talk about heat due to polymerization. We talk about heat due to evaporation. And we talk about heat due to chemical reaction. So we have all these things coming into play for us to be able to capture properly the physically reasonable model. We also have, in addition, the conservation of species. And when we talk about the concentration of whatever substance we're talking about, we talk about the equation of state, probably for an ideal gas, which is more commonly used. And then if there are suspensions or particles contained therein, then we also have an equation that will capture that. If that is agreed upon, then we have to look at what we have. The first thing is to see that the conservation of mass, we have only just one equation. It's a scalar equation. And then we have conservation of momentum. We have three equations. There's a vector form equation. Conservation of energy, we also have one equation. It's a scalar equation. Conservation of species also scalar. We have one equation. The equation of state of an ideal gas, we have one equation. And where there is suspension of particles within the fluid, then we also have one equation. So what do we have at the end of the day? We are talking about having a simplified model, but now it's comprising of 7 systems of coupled nonlinear equations. Okay, these are partial differential equations. They are nonlinear, they are coupled, so we can see that makes it not easy to track at any particular time. If that is agreed upon, we need to look at what are the model equations that we have and what are the methods by which we can solve such. Then we have these techniques. We talk about the Fourier series, Laplace transform. We talk about the perturbation method. It's very, very, very useful also.
Online. My network has been troubling me.
Talk about the traditional techniques, differentiating the quantities, and when Dr. Bibala was talking to us, spoke so much about differential inequalities. Okay, and then we have functional frameworks, which he also spoke about. He mentioned some of the functional frameworks. Okay. Now, if we agree with me on this, some of them. Thank you. Now, okay, thank you. So we now come to the background, another background information that we need to have, and that is what is the definition of computational analysis. We talk about computational. Out of all the methods, they are all useful, like I said, but for my talk today, emphasis on computation. So here we have identified that it uses advanced computing algorithms, simulations to process large data sets, and then model complex systems. What is the eventual outcome of this is to reveal the patterns that we cannot see physically, also to tell us the trends that supplies, and then to tell us some behaviors invisible to traditional methods. So it's very important that we understand what the whole thing is all about, and I'll demonstrate some of these things to us as time goes on. We now come to the computing devices. I mean, the traditional one everybody has here in this one is our laptops. We have laptops and use that to do our computation, and it's very good and goes at least to some extent to help us to do what we want to do. And then we have high performance computing facilities. This is also another area in which we need to also discuss, and which will be of benefit to us. The first one that I have here is one that I've used extensively, and that's Abdul Salam International Center for Theoretical Physics. And in that, nothing less than 15 times, all expenses paid. And so I've used the facility often. We also have one in the University of Cape Town, South Africa. I'm now Professor Arnold when he was there, Malan. We also have one at the African University of Science and Technology in Abuja. And we have these people also overseeing it. but we don't know Joe is in physics department UI, and also we have Clement Olina from ICT. We also have another one, the Federal University of Technology in Akure, under the German government. It's also available for you to also make the best use of the opportunity. There's one coming up at University of Ibadan. I was discussing recently with Professor Olubusuye on what was going on about this. I'm aware, but it's under the teaching school. So they are still working on it. They have almost not perfected it, but they have, I think the intention is there, which is good. We also have one at Tobafe Babylon University under the auspices of Professor Aderomi. It's also under the German exchange program. So let me give you a brief history of numerical analysis, because it's always important to know the origin, because that helps us to have a better understanding of where the whole thing starts from. Numerical algorithms are almost as old as human civilization. Why? Because if you look at what happens in the time of the ancient Egyptian, the Rhine papyrus in 1650 BC, they used some numerical, a device, let me put it that way, developed in one way or the other for finding the root. So we call it root finding method, find the root of some quantities, square root, cube roots, and all these things. So they started from there. And so it's something that is good for us to also refer to. And then we have the period of Archimedes, in which they also developed the method of exhaustion. And this is also useful. This was where they started all this numerical computation. And this has progressed up to the point that we now have what we call the development of calculus. And this came up at the time of Isaac Newton and Leibniz in the 17th century. So these also has helped us in developing complex mathematical models that relate to differential equations, that relate to integral equations as well as integral differential equations. I'm happy for the man who spoke to us, Abibala, was talking to us about capital, what do you call it now? Fractional. I mean, these are just evolving. These are set. They are recently evolving. And so, fluid dynamics equations are most naturally posed as a system of coupled nonlinear partial differential equations, as I've said earlier. And so, what do we say here? Fluid-based computational algorithms. It's very important for us, some of them. And the first one we want to mention here is the inbuilt server in packages. I mean, many of us are used to this. I only use Maple and Mathematica. More often, I use Maple. I mean, I have it on my laptop and I do some little calculations. But also, we have finite difference method, which many people do adopt, depending on the type of equation that you have to study. We have finite element method. These are all good methods for solving problems. We also have what we call the finite volume method. This method, I'm not sure of many people working on this in Nigeria, but I want to inform you that I have a PhD student that finished just last year. He has to go to Japan to be able to use the high performance computer to be able to solve all these problems. So this also is very trendy now. I think it's very good. So we have the open form solver, which you can get online. It's free of charge. And to develop your skill, it's important if you can learn how to do it. But I mean, if you want to really do the work, then you need to go to a center now. They have a license for you to be able to do better work. Okay. And then we have what we call the adaptive fluid foam. Then the multi-regional foam. What these things are, there are things that we can work with that will help our computation. We also have computational fluid dynamics, which most people are working on. But more importantly, people in engineering prefer to use this computational fluid dynamics. We have volume of fluid method, which is also available for a lot of us to be able to actualize. So one thing I want to point out, therefore, is to let us see that numerical simulation incur quite high computational costs. It's not free. I mean, you must have a license to use some of these high performance computing facilities. And at times, the simulation may go for months, may go for years. So we must have steady analysis. Okay. I hope Nigeria can get their own way.
Amen.
And then let me share one or two first-hand models that I've studied over the years. This will make things clearer to us. I think the first thing I want to talk about is, amongst all the work I've done, is micropolar fluid flow. Microsporal fluid flow are non-Newtonian fluids. Why? Because they are microstructure and there are also small particles that are oriented in the fluid. They are called particle suspension. They are inside the viscous medium and they can rotate and alter flow dynamics. So it's a very important. Sorry, I'm sorry about that. So these type of fluid are not very common, but they are available in the industry and they are very useful for us. So we need to learn more about it. And I've done some little work. So I want to concentrate more on this. And that's why I decided to give some first-hand experience of microwave fluid.
When I muted, it took me back to
Okay.
Exactly.
Thank you. So with applications in
take us back.
polymer solutions, we have application in lubricants and biofluids. These are very useful areas which these things are available. Okay. So the first thing we want to look at is the assumptions. So I call this problem design. Want to design something, want to design a problem. And for us to be able to design that problem, we must have some assumptions. So I take this as my assumptions. Suppose you have a steady flow, it's inclined, you have gravitational effect, you have all these things coming into play. And at the last point here is what we call the heat flux. Okay, it's the heat flux. But then when we talk about the heat flux boundary condition, what we are talking about is talking about the Newman boundary condition. Just in the question. Okay, so now we have to look for the method to solve the problem. And the method used in this first model problem we are talking about is to use, the method is partial to ordinary derivative using singularity tools. I'm not able to bore you because there are many people that if you're interested, you can see me later, we'll talk about it. Then what is the algorithm that is used? That is the shooting technique. Okay, and there's a longitudinal method. And this is performed also on making very simple problem. And I can assure you that this has been published. And we published this in the Fusion Foundations. And these are the details. And 3 of us are involved. Back today is in South Africa. Oh, thank you. You know, Professor Martin, thank you very much. And then this is my PhD student that finished under my tutorship. And so we wrote this together. And okay. So let me tell you another thing that I've done. Another model is another model too. You can see I've changed. Still on that same type of problem I'm looking at. I've only changed assumptions. But look at it now. The last one was inclined, but now it is vertical sheet. Change. So it's a new problem. It's a new situation. And some of the things have changed. And if you look at the boundary conditions, you know, we have a prescribed surface temperature here. And then we have also a prescribed heat flux here. So, and then when we did this model, we were able to come up with the method also is the same, as simple as APC. From partial, we reduce it to ordinary, and we're using similarity tools. And then the algorithm is also similar. It's the same algorithm that we use here. We're able also to get this published. The 2 of us, my former PhD students, now at Federal Polytechnic, Labo, we did this together, still on microwave fluids. And this is what we have been able to accomplish. We have the 3rd model. You can see I've changed the visions. I'm letting you know that all you need is not to change the assumptions, and you must be first. Because you have to do the literature review in line with that new set of assumptions. So the literature reviews was different in each of the models that we have considered. So here again, we have all the assumptions stated. And if that is agreed upon, then the next thing is to look at the method. Say the same thing. We are reducing the partial differential equation to ordinary by just having similarity transformation. Okay, this has also been published. These are recent publications. This is published in 2021. Okay, and here again, the 2 of us collaborated to get this work done. We go to the next model. Another first-hand experience is model 4. Here again, we have the problem design. We have all the assumptions that comes into play. You can see these are all the assumptions. It's completely not exactly what we had in the previous ones. And here also we look at the same method of solution. And here again, we use the same algorithm, shooting method. I've explained this in details in one of the papers. And then we have here also published locally the Journal of Nigerian Mathematical Society. As a former editor, so I already separate the journal and publish there to check my citation, go to Book Scholar and check my citation. The highest citation I have is the paper I published locally, not to go international, locally, and I've cited on people in the whole world. So I encourage you also, if there's something wrong with publishing locally, but don't make all your publications so that you'll be known internationally. So it's a good thing. So we got this too. And then we change the model again, and then after some experience of model 5. And what we did here also is similar. We looked at the design problem, look at all the assumptions that comes into play. And here again, the same method, the same algorithm. But now this one is different. We use Gallatin weighted residual method. This is different from previous ones we use here. And then we were able to also get this published in the International Journal for Modeling and Simulation in Taylor and Francis. But this time again, we brought in a young collaborator. That's A.T. Adeosho. So we need him to know what we are doing in this area so that we can spread our tentacles. Let's look at another model 6. We have the problem design. We look at all the assumptions that we need to put into play to be able to solve this problem. And this is completely different also from what the previous one. Like I said, it's like with the available, so you can also go back because of the limited time I have. So here again, we approach it using the recruiter method. I remember the first time I learned about this recruiter was through Professor Fatula, who was at Uniben. And he was inviting us to come to Uniben to come and develop our skill. That's in the early 90s. He was also one of the beneficiaries. Today, it's no more. He was at that time working at the National Mathematical Center. I had to travel all the way from Abuja to Benin, back to, go up and down. Was easy, and the roads were not so good. But thank God I was able to also get some knowledge. This also was published. This is 2023. This is a recent publication. Here also we brought in another young collaborator. And here we have also training him to see how we solve this type of problem. We also proceed to another model. This year I'm going to take some time, explain the details, because these other ones are not brushed through for us to have an idea. So for this first-hand experience model, but this time we're looking at stretching in 2 dimensions. All the previous ones have been 1 dimension. The stretching is in 1 dimension. So we look at it here in 2 dimensions, and these are the axes. I've chosen our axis. So it can be stretched here. We can stretch it on this side. We can stretch it on this side. And to do this, it's very simple and straightforward. And here, what we have is this is what I'm designing. And this is the design assumptions. So if I have all these assumptions put into place, this problem is slightly different. Look at it. A dual extended surface. It's different completely from the previous one. Okay, that we have considered. But most of the other things remain the same. There is no chemical reaction taking place, so no concentration down. That's what we are here. We have linear heat source. We have non-linear radiation term. We have no viscous dissipation, non-porous sheet, and everything come into play. So what do we see here? Now I've decided to show you the equations so that this you can appreciate the beauty of the mathematics that is involved. So here we have the continuity equation because we said it is incompressible. And so the density is a constant of this motion. So it becomes simple. It's like this. And then here we have the momentum equation. This is the electrical field that comes into play and is defined thus. Okay. And then we have the contribution from the spinning of the particle. And then we have the temperature equation. Okay. And here, this is purely Newtonian fluid. Okay. But some I did cast up. See, I mentioned, but this is Newtonian fluid. And here again, what did we do? We decided to make it 3D. Look at it. All the previous ones have shown you were 2Ds. So but now it's 3D. And then also we have the micro components to also be in 3D. But one important thing I mentioned earlier was the Kosinski approximation, which is from the boundary layer problem. So that made the equation to become simplified, and that's what we have for God. So how many equations do we have? We have these equations. We have one equation here. We have second one, third one, fourth one, fifth one, sixth one. Then the next thing is to try to look for the similarity relation that we can bring it to play to handle this problem. And if we look at it, now the partial differential derivative using similarity, this is what we have. This is third order. You can see this is third order. This is now more of ordinary differential equation. This is third order. And here is also third order. Okay. And this second order is also second order. And then the corresponding boundary conditions. So it is important for us to know that though we are reducing from partial to ordinary, then the order increases. So what do we have effectively? Then we have to think of how to attack the problem. And then the first thing is to also use the shooting method and the reticular, because it's not we have explained that to you now in due course. First, transform to first order set of 12 simultaneous differential equations. So you can see that everything that you want to have been doing, modeling of malaria is always ordinary differential equations. So we need to have succeeded in reducing mine to ordinary differential equations. So that I can track it. So but this time we have how many? We have 12. And then we have to look for the iteration. Don't forget it's now the boundary conditions, the initial conditions that is constituting the problem. And these are the ones that we do not know from the definition of the problem. And so we have to use a shooting method embedded in Maple software to be able to find these initial conditions. Then the developed code for the present problem has been implemented using symbolic computer algebra tool of Maple 16. And I think the last one I used is Maple 24. So that's advanced so much. Then this method is found to be stable, reliable, accurate for tracking non-linear problems. We adopt different values, looking at what others have done earlier, and from there we're able to get the values to use to for computation. And the next thing is for us to validate our scheme with what has been done earlier, but that has in the literature, so that we can be sure that what we are doing is consistent. And so, therefore, this work has also been put out. This was 2024, it was published 2024, in case studies in thermal engineering with this young man. And what is important about this is that bi-directional and precision model. All these about the problems we are talking about, they symbolize what happens very close to the surface. This is the surface, what happens very close. So when I say infinity, when you look at my boundary condition, I say infinity. Infinity is a number. Infinity is, so you say, what is infinity? Infinity is in the context of what you are doing. I can tell you that 1 million naira is infinity. Why? Because if I look at 1 million naira in the context of 50 naira notes, and you go to the bank and they give 50 naira notes, 1 million naira, and I'm telling you, you will reject it. Why? Because it's infinity, it's too large. You need to gather must go 4 or 5.
When we went to the wedding, they were giving us bonds.
If you give me
100 naira, we spent. We counted everything. 50.
So infinity is reality, and the most of the people that will be, so you have to break down and the value of infinity. So now, what do we take away from all that I've said? We need to realize the fact that how to solve one problem demands critical thinking. We have to think deeply. We have to search literature. We have to look for things. So critical thinking is very germane. It's not trivial. And many people are distracted nowadays. So this critical thinking becomes very important for us to put into perspective. Then you need to be able to do model development. You need to learn the technique for model development. And you can't do this alone. I mentioned here that we need to do collaboration. I remember when I first started my research, it was single authored. Then that was the way we were told. You have to prove yourself, you have to show that you have to play it, but times have changed. You can't do that again any longer. So you need collaboration. And I feel that this issue of collaboration is important. Go for conferences, interact with people, don't just sit down because you came for a conference, meet people, talk to them, say hello to them, and know who they are, know what they are doing, get familiar with them, and the sky is the limit for you. So I get this pictorial representation. Many of us have traveled out of the country. When you look down from the window of your aircraft, you will see your plane being dragged by just a small car. So that's why about this. You don't have to do it alone. Even the big guys, look at this big guy with more than 300 passengers on board with their loads and everything. He needs help from just this small car to push it out. Many of us don't know what this means. So it means that there is somebody who can mentor you. There's somebody who can help you interact with them. Okay. So another takeaway is to know that the benefit of solving real world problems. I mean, this is important for us to take home because when you solve the real world problem, health development comes into play. I never knew I would be in health and not be invited to come and talk on health issues. But if you are invited to come and talk on malaria, you're not able to talk on malaria. But I talk on some other things that has health issues. Okay, and this we're talking about also has to do with it. But we're looking at what happens on the boundary of any sheet, of any surface of an aeroplane moving. We are interested in because of turbulence. We need to be able to study what goes on around the boundary when the plane is moving in the air. Or when you look at an aeroplane in the water, what to see. So we need to study what happens around it. Okay, so with the health implication becomes we'll be able to make prediction because safety is very important. In any aircraft, the important thing here is the safety. So in everything we are doing, safety becomes germane, and you need to take note of that. The cost effectiveness is also very germane. You cannot run away from it. Because some of the simulation may not be something you do on your laptop for 3 hours. Some you may have to spend months. But the ones we have here, some I was prepared to be able to do when I went to ICT to complete the competition. Now, these are members of my research team, the modeling of complex systems research group we have at Okpata Naulawa University, headed by Uncle Seb. Yeah, and I'm the team lead and the principal investigator. He did his PhD under my supervision while I was in Unilag. He's currently at Federal University at Bella Polytechnic now. This is just my recently graduated PhD student, Sunday Opadero. In his own case, because of all this health education and everything we are doing, he's working more on polyurethane and polystyrene. I mean, these are things that, like the cup that we use to serve you, these are foams. He's working on foams and they cannot run the model here in Nigeria. So we have to help him to secure the DAAD to go to Germany, 5 months, and be able to carry out some analysis to be able to get his work done. And now again, we are trying to work. He has finished. We graduated in December. We are hoping that we'll be able to get an APH for him so that he can also do his postdoc because some of the facilities are not working properly locally. So you need that collaboration. This is another young guy, Sulaiman Salam. He's just been pronounced professor. One of the federal universities in Ekiti. Yes, in Ekiti. But formerly in Bowe. So we have been working together. Go to my Google Scholar, you will see collaborating work with all the people that are on here. But we didn't end it there, that would have been okay, but we started to start what we call the International Conference and Advanced Workshop on modeling and circulation complex systems. Because I do more of complex systems, and so we have Dr. Irek Anjami, who coordinates the workshop, and we have Clement Olima Idetli that coordinates the conference. And now my group said we have seminar series monthly, and I coordinate that, and I also take care of the local organization of all our conferences and workshop. So this is my baby also. So I'm trying to teach this to see how far we're going to go. So far so good. We have met twice. We met at Obasanjo University in 2024. Last year we were hosted by the PG School and UI. So we're at UI for 1 week. And now we are going to Abuja. We want to just still go a little bit outside the Western zone. So I went to Abuja. We are just trying to consolidate. I don't want to put it out yet because we are going to send out information in due course. So this is what we are doing, and this is how it has gone. And like this.
Okay, so do you
Sorry,
have
good
any?
afternoon. Yeah, Alhassan Tijani is online now. I think I can present now. I'm ready.
Okay.
Having hello.
Participants,
Yeah.
right? We have a timetable that you also have with you, and we have announced to you that the next panel session starts by 3, which is according to the timetable that is with you. So please, it's keynote speakers now that are speaking, not parallel session, please. I wouldn't appreciate interrupting our professors while they are doing their presentation. Please, we beg you that you stay tuned with what we are doing according to the timetable. Now we want to give room for questions and answers based on what our dear professor had presented. So we would appreciate if you are online and then you have questions, please you can signify our media is able to track everything that happens over there. So while those of us who are seated here also, all right, I think it's time to engage. Yeah, I know that people like who are younger people here would want to see how to take it off from where old people, because when you already now have somebody that is professor and is a professor. So you already know that we are dealing with the generations that we were just coming. So now you need to really tap as much as possible, all of us. So please let's ask questions, sir. Seniors, okay. Prof said all of us are old because when they ask you, they will say, "How old are you?" Okay, fine. But I don't know how to call Grandpa senior. But Prof said, so I will use Prof's fans. I still don't know how to say it. Okay, that one is better. My elders. So thank you. So please let's get as much as possible from from him while he's still available with us. Please, I think it's very important. Question, please. Question. Don't tell me I'm having one hand. Okay,
Mr. Dolapo,
that's great. So
Mr. Dolapo,
I'm moderator.
we have one question.
1, 2,
Where is it?
3, 4, 5, 6, 7. And then 12. Yes, probably. This question also gives you.
We have one online, right?
Yeah.
Can we online? Let's start with the online.
Okay, let's start with the online, please.
Mr. Tijani.
We have a question, please unmute.
Mr. Tijani, you're unmuted. Please, you can ask your question.
Okay. Good afternoon, sir. Sorry, can you hear-
Yes, we can hear you.
Okay. Okay, thank you for the wonderful lecture, sir. Sir, my question is, I don't know, is there this your area? Is there any training you can give to somebody in mathematical modeling to enhance mathematical modeling of infectious disease rather? To like maybe the area of computing or any other area you think that can help somebody in mathematical modeling of infectious disease? Thank you, sir.
Mathematical modeling across so many areas. Malaria treatment is just one of them. Okay? And so I don't know what you really want from modeling. If you are working, then you come and discuss with Professor Bakari, who is an expert on diseases and all these things. I'm not looking at it from that perspective. I'm more interested in the modeling of fluid flows. That's why we call it. It's also a complex system. It's very complex. It's not trivial. And so I don't know how best I can be of help to you. But one thing I know is that Icambia is a very good avenue for you to be able to develop your skill. So if you can find the time to come down, I'm sure you'll be able to have a big interaction with people who are relevant to your subject area. Thank you. God bless you.
All right, sir. Thank you, sir. So we start with our separate.
Thank you very much, sir. And while you were talking, sir, you mentioned the similarity tools. So you said it moves from a partial to ordinary. Yes. I mean, solid structure. Yes. So we always use a Gallatin method to move from that fourth to ordinary. I want to ask, is it the same thing with that similarity tool you use? And if it is not the same thing, what is that similarity tool that you use if I can use it in my own user? No, there is no problem. The similarity tool we are using is along the line of which I'm also training one of my young ones. His name is Balao. What do you call this name? He stand up for recognition. He wrote his project on similarity using group theoretical. Am I right? And then he has to, play around. So this is a very good person you can talk to. I've just groomed him, and like I said, I'm getting old. But what you don't want to learn, so that you know what you are doing. So he did a perfect job for his project, and he had an A, and it's a 3-star general. So looking at him. I hope that answers your question.
Sir, good afternoon, sir. If I am really fulfilled in the presentation, I have my MSc in computational physics, and I want to actually ask, one of the tools we use is for GCUTA. When we're trying to stimulate using MATLAB and vary the. But what I want to say that their numbers, the more in the case of maybe you are making a publication in that aspect, and maybe the computation device you use may not be able to take live link. How can we include that in case of a complication in that case of modernity?
Yeah, thank you very much, sir. I'm very happy to have physics background. It's also using computational tool for the study. One thing I want you to realize is that our laptops have limitations. That's why I brought it up. I have to let you know. We all have laptops, but it depends on the strength of your laptop. Okay? And so more often than not, and that's why I told you many times I have to go to ICTP. And I said I've been there minimum of 15 times. All expenses paid, either as a regular associate or this, and that's why I went to Madras, because they have these facilities I can use. They have computers. But if I stay back in Nigeria, I'm not sure I'll be able to progress where I am today. And let me tell you the story of my life. We started computation using punch cards. I did my PhD in the 80s. There was only one computer in the whole of Aberdeen University. Only one. They call it a mainframe. So you have to take cards, you have to punch the cards, and they have to put these cards in the computer and they run it. If someone mistakenly, the operator mistakenly typed the wrong thing, you are sued. You can see what we went through. It's a great ordeal. And I have to translate from that to modern day computation. And that means you have to look for what you want. I know what I want. I can stay here with these punch cards. And then I started looking for opportunities. And the first opportunity I had was to go to ICTP. I had an opportunity to go to Spain. Professor Abban that came is from Spain. I had the opportunity to go to Spain, but I couldn't go because they could not give me full scholarship. But ICTP gave me full scholarship. And so I went. And then it was then I said, oh, I'm here. I'm seeing computer for the first time in my life, the desktop. For the first time, that was 1992. I said, I don't have to operate this thing. So I have to ask them, please, how do we, and they tell me, put down here, hey, okay, I know it forever. Once you do it, I know it. And gradually, I got to know how to, I learned how to use LaTeX for the first time in 1992. I always give everything to my typist. That is why I type my paper for me. You type it, I do correction, I publish it. But things are changing. I have to move the time. And so, from there, I now have to use the desktop. From the desktop, gradually, I say, what's the laptop? My laptop. Oh, what's the size of your laptop? Okay, my laptop is limited. I cannot go beyond this limit. Oh, then I have to look for another person to go back abroad. That's how I've been going about. To let you know, because of that, all my postgraduate students go abroad. My first PhD student was Agadi, took him down to ICTP as of 2003. As a young researcher, all the expenses paid. Come and see what we are doing, how they are doing it. And then after that, you have to go to Israel for another 2 years of postdoc. Strengthen him. And I've just told you also now that this is not the PhD student is also going abroad. Because that's the only way you cannot sit down here. Why sit we here till we die? You have to move. And you have to look for connection. You have to, meet people, talk to people, ask for opportunities. People here today. Somebody has gotten an opportunity to go for MSc abroad. Let's appreciate God in His word. Today, nobody apply. That's what we are here for. We know them, but you may not know them. But I've been in the system for more than 43 years. You know, I started as my citation was read. I started in 1984 as a lecturer. You know, but I was been teaching as a compa, knowing how to do the thing. So what I'm saying effectively is that we just need to encourage our PhD students to go out. If they don't go out, they can't pick it. You can't get it here. I'm sorry. You can't get it here. You don't have light. At that times, light has gone. So I want to do a simulation that will take almost 24 hours. How do you want to do it? There's no light. And so when you send this paper out for publication, they will ask you, where did you do it? Anytime I write, I put there, I visited ICTP to do the approve, accept. They can't credit it. And they know that the facilities there, that whatever you have done, justify it. So you need exposure. That's summary of everything. You need to go out. And the young ones must look for opportunities to interact. Go out. If it is 1 month, 2 months, you will see it. Your life will be different. Because you will have opportunity to see high computing facilities. That's the best way. But I hope what I've said so far is just gives you a picture of how some of us evolved over the years. So we will be here today. Okay? All will be well. Why sit we here till we die? Take note of that.
Good afternoon, Prof. I'm so happy to be under your presentation today.
Thank you.
And my MSc, I did a fluid mechanism.
Fantastic.
Yes, thank you, sir. So during the computational analysis, I use the mathematical tools, MATLAB. But when you were talking the other time, you said MIPU. So, Prof, sir, I want to ask that what is the advantage of MIPU over other mathematical tools like that MATLAB, like Mathematica? Then is there any embedded, like the MATLAB, there's embedded code, which is B4C that I use for my listing. So please, I want to know the advantage of MIPU over, because I like to use that MIPU. You know, there are some of that they say they want you to use this particular software, either Mathematica or this. So please.
Yeah, thank you very much for that question. I think the way I will approach it is to say that it depends on what you are working on. From my own perspective, take for instance, my PhD student that just finished is using MATLAB. I'm used to MIPU. I can't change. Because the moment I went to ICTP, I was introduced to Mathematica and MIPU. That's what I've been using for my research. So, but then I just fell in love more with MIPU because I have some inbuilt software that can work around it. And I said, oh, okay, let me stay with this. But my PhD student worked more with MATLAB because the first problem he was looking at is polymeric flow, not what I did. Because I make sure my PhD student are not doing what I'm doing. That's the only way to have tentacles. Okay, so, and that has helped. So, I don't think I will say one is better than the other. It depends on what you are looking on. What are you looking for? What do you want in that software? What is the software that you demand for? that will help me to solve your problem. And many of the things I got, like I said, it was going to ICTP, I saw many books on Maple, and I saw the way they wrote some programs, some codes, I started studying them, and then started using them. That's how I ended up with at the end of the day. So it depends on what you are working on. We may discuss after this and then we'll be God bless you.
Right, good afternoon, Prof. Thank you very much for the presentation. So my question is around, I'm interested about how the problems are being formed. If you could walk us through, coming up with a problem, for instance, some of the models you presented, what are the motivation behind coming up with such problem? Are there things that are observed in real world situations and stuff like that? And also my second question would be, currently as we have now, what are more like a prospective future we can see in fluid, particularly I'm more interested in the biological system, in fluid flow in biological systems. So, yeah, something like that. What are the prospective and things people can start looking into here? Thank you, sir.
Thank you very much for that question. I think one thing is very germane. And that's the fact that in everything we do, we have you must have a motive for doing something. And I explained to you earlier that in most of my research has been based on the student that I have. And I don't impose my work on them. I only guide them to have an idea of what I'm doing. And then I give them the leverage to pick whatever they want. So it's what you are interested in. That what's of motive to you, that thing that motivates you. Like Fatumbi now was more interested in the problem I just discussed today. And that's why we have been working in that area together. The PhD student that finished is working on polymeric foams. And if I show you some simulations of how the foam evolves, when you have hard foams, which is good for your health, or you have softer foam, which you sleep on, or this one that we have here, there's a foam here. Do you know there's a foam? To pad this, there's foam to pad this. These are all foams. He said he's interested in that because he had a chemical engineering background and the long process. I said, okay, so we have to read it together. But now I'm going to supervise you to be a master in that thing too. But I don't know it. So he becomes my motivator. And then you want to discussing with me, and then I ask questions, and then because of my own wealth of experience. And so that's how I ended up in different things. Actually, my PhD is on chain branching, chain breaking kinetics, chemical reactions into flow. So that's why concentration, I still mention concentration. Oh, there's no concentration in this. Oh, this one has concentration. Because that's my primary area of interest. So that's what is driving all the areas that they are all complex systems. So all my PhD students are independent. And that's why I have a large collaboration with people. So that's why that is so. The second problem you are raising is so to formulate any problem, I think I always tell my students, your mentor should be able to guide you. Okay? So like my own guide is to say, okay, what are you interested in? We sit down around the table with serious problems. You tell me what is of interest to you. And then, but all the papers I wrote at the early stage, let me tell you how I got the motivation. Because of my chemistry background, I'm more like do some chemical reactions. Look at it. So I look at what others have done, pick a paper, okay, and that's what helped me to be what I am today. This is here with myself. I pick somebody's paper. This paper is in my area. I read it. I can't understand most of the things contained therein. Then I know I have a problem. Because this is my area. And I cannot read beyond the introduction or the other part of the modeling. Then I have a problem. So that was why I said to myself, use myself as an example, that I got my PhD in 1989. And I did not publish any paper until 1992. Why? Because I bet one. No, until 1994. Sorry. I traveled in 1992, wrote the paper and everything, and then published in 1994. So what I'm trying to say in the fact is that I got to a point, I look at myself, have I arrived? I don't think so. What am I doing in Nigeria? I need to go out. So I looked for opportunities. And eventually I went to ICT for 4 months for postdoc. So from there, I now said, okay, I wrote a paper, I took a paper, I started working on it. I saw the author was around at the center then. Oh, Prof, you are the one that did this work. I'm interested in it. Can I modify it? And then we started discussing. And before you knew what was working the thing progressively, in the way I understand it, I'm not interested in, I knew what he did. I'm not interested in his technique. I want to use my own inequalities, differential inequalities to solve it. And I did it. I showed to him. He was like, oh, you're a smart guy. I don't know if I'm smart. I'm here. I want to develop my skill. So from there, I got what was going on. And then I asked, you are the one that has been mentoring me, guiding me, providing this. And this, he said, no, don't put my name because the paper is similar to what I've done. If you put my name, it was like a repetition for him. Now, as you go and publish it, I said, thank you, God bless you. But that was my first time of looking for a collaborator. And then I pushed it out. And then I asked him, where do you feel like I've thrown this paper? He said I should throw it to University College London. I was like, my heart beat. University College London. I don't know if I've arrived. And I did. And they gave me 4 reviewers. And it was hell for me to answer all the questions that were raised. But in the course of attending to the issues raised by the reviewers, one of them was adamant that what I quoted from the previous paper is not correct. And that's what delayed completion of the. You mean? People are very sincere. That's what I do often. I give you a guide, I give you a direction. Get me a book on differential equation. He said, I should read that book and it will help. And that was the strength of the paper at the end of the day. I had to sit down a whole book, study it, understand it. He was the only one that opposed the conclusion of the paper. That if I don't change that argument, we won't publish the paper. And I said, okay, if this is the case, I have to. And he said, if I'm going to add anything to that paper, it should be a remark, and it should be no more than 2 sentences. You know what that means? You are giving me a book to read, and I have to read this book, understand it, and then summarize it. It took me a hell of a time. Eventually, I got it. What I to him, and I don't forget that time, I'm talking of 1993. There was no internet, it's just evolving. 1993 internet was just evolving. They have only one point in no way where you can send messages and all this. It was happening. So I had to send it by post, and then it took some time, and eventually at the end of the day, the thing was got to the editor, they forwarded it to him. It's okay, 2 sentences, he was satisfied, but he wanted to know if I actually did the work. So one day I just went to ICTP 1994. And then I have the email, I forwarded the email. I said, I've sent this thing to you a long time. What is happening to this paper? And he said, oh, can you please resend that 1 page I asked you to write? The 1 page. It's Nigeria. I'm here in Italy. I did the work. I read the paper. I just went to the shelf, brought the book out again and summarized it. 1 page. I said, it can't be exactly the way I wrote the first version. And then I wrote and forwarded it to him. And let me tell you the good news. The following day, the secretary at the institute just called me and said, Sam, I said, yes, you have the fax message. It's a fax message. I know message. But I don't know what is a fax message. FAX. So I followed that to and then she brought that to people and then gave it to me. This is a fax message. So I'm happy I know what a fax message is. And it's a good news. Your paper has been accepted for publication. Bravo. I got my motivation because I was at ICTP, I met this author, and I discussed the problem with him, and I approached it from another perspective, and now I brought out a new idea that is different from what he was suggesting, and I was happy for it. So what I'm saying is that you can just talk to people, but when you read the paper and you don't understand, talk to the author, call him, send email, but this is available now. In those days, they were not there. So you can use that avenue, to get information and then improve on your experience. But more importantly, make sure you at least about 2/3 of your publication should be outside the country. and in good journals. It's very important because that's where the citation will come from. Except you are citing yourself locally. Because I don't know most people that have cited my work. I don't know them. I just put them there. So thank you. God bless you.
Right. Sorry that I have to come in, Prof. While Prof was speaking to us, somebody very important was came in also, and she's very busy, as you know that, like Prof was saying, it's transition period in FOA, a lot of activities ongoing. She's one of the persons that make you to be able to sit in this auditorium, because if she says the brain, yes, it is the brain behind this auditorium where we are all seated, right? From yes, I mean from the scratch, and even now, so this is director of Advancement Center, Federal University. Oh yeah, Professor, I'll call the name before. Professor Olubukola Onisola Onyamoye. I think she just say a word to us before she goes, a good will message. Professor, please, you will permit that to do that. Thank you so much. This Professor Koya.
When you talk to mathematician, you have to be very careful. Professor Koya, as I am standing here, is probably calculating the speed with which I move to the front, calculating the hours and dividing, square rooting everything. Professor Koya, you're welcome, sir. I have met with you. I was at the University of Ife as Commissioner for Environment at one of the conferences if representing Aredberg that time. You were there. I had a professor of mathematics at Ogun State University where I schooled. One time long ago, he gave me a ride from Agogoyi. That was when New Ife Road was being made. That was the old Ife Road where we used to pass. But the new Ife Road came where we were going to have to come and boycott Osun. And then while we were on the way, my mathematics lecturer, who also lifted my brother, gave us a ride. You're going to Osun, right? We said yes, from Ogun State University. 83. Began, and I thought he was over speeding. Perhaps he looked at my face. I said, young lady, you think I'm over speeding? He said, the road is a straight road. I can move at a minimum of a speed of 120 kilometers per hour, calculating the total number of vehicles that was coming in the opposite direction. And then when we got to a place, he overtook a vehicle. Before he overtook, he just in his 404 moved and said, the car, if I may guess, is coming at a speed of about 80 kilometers per hour. So you see why I'm afraid of mathematicians. In about 2 seconds, given the accelerated position of my car and the point that we are overtaking is like about 19. This other one is still like a quarter of a mile away in 2 seconds. And then that's of a Bible junction. And he said, did you pass your physics? I said, yes. I said, yes. I said, so today, did you pass your mathematics? I said, yes. He said, we are going to apply Pythagoras theory. Well, there's a you see, all different the new true road, that's the opposite and the high desert. If I move through the hypotenuse, the sum square, Pythagoras and the sum square of the hypotenuse is equal to the sum square of opposite and adjacent. Said, that's good. That's good. He said, therefore, we cannot move in this way. We are going to move to cut because only the shortest cut is a straight line. And we are intersecting at Osun Junction going to Ife. Since that day, that was the last lift. People thought mathematics is abstract. They think physics is abstract, but indeed, it is the application to life. We just had edutainment last week, and I told people education, technology, and the society only moves around with entertainment. When you have these three things together, you have mathematics, because that is the calculation of the actual reality of life. You all laughed when I talked about my professor, but sincerely, isn't the Pythagoras theorem the reason the decisions are made by those who make roads? Isn't the reason and other theorems, when you're talking about angular and computational, whatever you're saying now, isn't that a reason why you bypass Mercy and you take a road and you look at the value, you avoid it, and then you go through some longer routes to get to the destination, probably at a zero. So please, mathematician, computer scientists, computer information individuals, physicists who are made up, come there. Be proud of yourself. Tell everybody that mathematics, computer information sciences, computer and computational sciences will run the world. Those who make things for us, those who go to who goes at the speed to go to the moon, those who go everywhere, and those who calculate and make things happen are you. You can calculate the speed, you can calculate the ray of the sunlight, you can calculate and know how much effort you're going to get, even what we are using, and how much we are able to charge the solar and all of that. You're too important to fit in it. Don't what you it. Without computational sciences, things will not go right. Situations are not working. Things will not work. The frequency at which this is receiving sound and sound is going into this system. The second, that is why sometimes when you see television or you will see my mouth moving slightly faster than it is moving on the board there, because the few seconds of delay is this transmission period between the speed of sound going into this system. And these things are made possible. We are the end users. But don't joke with the microbiologists, because we are still at the It's nice to have listened to the way you answered questions. And I want to thank you for that child I'm going for mercy. I apologize for my not being here since Monday. I was just telling him, Director, that if I came here, half of your listener will not be here. But over the weekend, I had flu. In fact, I think gently there's some change of weather, but some COVID in the head, which is no longer powerful. The immunity of the body is able to crack it down as microbiologists, but it's there. So watch out for the flu. I didn't want half of your audience going to be here. Because I came on Monday. You can then begin to calculate the speed of which the virus. Like the total number which are in trillions. And you not can't small you that because it's viral exchange. For being here. And thank you for motivating us. I think I went to a degree of functional science. What will I do? Thank you very much, Ross. Thank you, sir. I appreciate it. So, and thank you. The wonderful This place is a story of what you can achieve, whatever you choose to do. No man, no king can say you name. The university cannot do it all by itself. I just had a dream and I told the VC, I can raise money and build a center of excellence, and where we all can gather together and have conferences, and at least let it be a little bit presentable, even to foreigners. Let's have smart boards there. Let's have projector elbows. Let's try. We will still try and improve our electricity to have solar that can run this place without the help of the university. God did it for me. I gathered him. I built this place. Whenever this conference center, you see what? When you have a boss, bad or good, and this one is if he doesn't give you the impetus to run, you won't be able to achieve what is on your mind. Because he said, Madam, go ahead. See what we can do. And later he confessed, said he was just thinking, by the time she does the foundation, she'll be tired. And we'll come to our end. When the last time I told him, I said, we are moving. He said, did you import the building? It took for like 2 or 3 weeks. Before it came in, the structures were standing. And then sometimes ago, he went away. Before we knew it, to go from there. And we began to do the little we would do. You could do your little remain much. And this is where we are all sitting here. Then I approached my colleagues. I said, no amount is too small. Senators contributed over 3 million, 50,000, 10,000, 20,000, 100,000. I added it to about 90-something million that I got from outsiders. And then this place was built with the help of the directorate and ourselves on Mr. Elabo online, and then they are online. God did this place for us. We are looking for how to improve it, to improve the electricity. We are here today. We will be greater tomorrow. Yes, we will be. Yes. Thank you.
Center. And now, going to call all the professors in the house. Please, I want you to now take a picture with our director, and then please let's do that. Professor Ideji, Professor Olubusoye, Professor Mrs. Okoya. Where's mom? Okay, good. It's a great one. I think that I'm learning a very big lesson from the director of Advancement Center, and that lesson is that you do your own bits, as she has said, do your own bits. If she didn't do her own bits, I'm sure we'll not be able to use this place. If this place is not like this, we will not come and sit on the floor in the bush in this place. But now it's here, we are using this place. Very beautiful. Yeah, 4 months completed in 4 months. She learned it. That's a very good. And also another thing I'm saying is that you must learn to see good in every place you go to. She saw that she can bring us something good, and now see it's not good. It's very good. If it's something good, you can't bring it out. Right? Your mind must also be good to see something good. She has a good mind. That's the meaning. So we really appreciate all this that you have brought to board, and for allowing us to also be practical of this place, to use this place. Thank you so much. God bless you, ma. Yes, a good one. Wow, that's a good one. That's a good one. 2014, right? So when maybe 2034, I'll say, yeah, I saw it. By that time, you say Professor Lashuk, I say, yes. All right. That's a very good one. It's a good story that they are seeing themselves again, not where they were before, or meeting at higher ground. They are both professors meeting, and that's a good one. All right. I'm going to hand over the mic to Professor Okoya again, who has, it's good. While they were talking, I just got to realize that. One other thing you want to see here. Okay, Daddy has been talking. But I think it's my bad. I should have done that. Daddy decided. I'm not sure, Daddy, you married Mommy as a professor. So, Mommy, I want you to do something for me. I was just asking that. I'm sure you were not married as a professor. So you see now, Daddy made a professor out of her. See now, are we not good? Are we not good? See now. All right, thank you so much. So I'm going to hand over the mic back to him to finish the job, and I believe you're enjoying it. All right, thank you, and stay tuned. Okay, so going to the next question. Thank you, sir, Prof. That's wonderful presentation, and you have done a lot of mentoring as well. So we appreciate it. So your family here is a blessing, and having you around now is also a blessing for this generation. We appreciate you, sir. I just want to ask a few questions. You have answered some of our questions from a physics background, engineering background, chemistry background. So maybe from a differential equation now. So this my question is coming because of the privilege that I've had to work with some of your mentees that you mentioned, Fatum B, Salawu. So I want to talk about this similarity transformation. That is what you use in this work. And I see that there's a link group symmetry transformation, and there could be some other method of doing this transformation. So I want to ask, that's my question number one. How do you know what to choose? Or all of these transformation methods will do the same thing? Because I see that this transformation, what they do is just to transform the PDE to ODE. So that is the first question. The second question is also in that line. When you transform PDE to ODE, I am of the opinion that you are about to lose some information because you are reducing the other. You are reducing some things that you have captured with the partial differential equation, because you are in the partial derivative you have there. You are doing it bit by bit, summing up to form, but now you have ordinary derivative. So I believe that there are some information that maybe have been lost in the transformation. So my question, if there are any, how do we account for it? Because we are now summing OD instead of PD. So that is question number 2. Sir, I hope I'm not, it's not too much. The third one is also in that line. I see people solving not with high performance computing, but they just use some semi-analytical methods. Like I just mentioned perturbation method, some use the computation method. And I see them that they will still transform to D before they use this method. And I see that this method can be applied on the original partial differential system of PDE that you have. I see that this perturbation method is without first converting to ODE. Why do they need to transform the ODE before they apply this method? Then the last one, I see that one of your work that you presented is on a stretch plane. Yes. So I see that I was somewhere when somebody was talking about inclined plane, flow on inclined plane, and a horizontal plane. So what I see is that he presented the model, the flow diagram for both. But to me, I said, no, can't this inclined plane generalize the horizontal plane? Because only the difference I see in the diagram is just the angle. So if I reduce the angle, the inclined angle to 0, I have this. So perhaps maybe the velocity will change. I say, can't this generalize so that I just have inclined plane, and I say when my angle is 0, then I have flow on horizontal plane. So these are the questions, if it's possible or not, sir.
Okay, so let's take it one by one. Okay. You have read so many things. Let me start with the first one you mentioned. You know, like I said to one of the people that asked the question, this group theoretical method for looking for sex similarities is very deep. You have to learn it. And like I said, I have a previous student that I have to sit him down to train him to know how we do this type of thing. It's not automatic. If it is not self-similar, then that's some people do some work that's not self-similar. And at the end, I just laugh. I mean, this one cannot say. But depending on who's the viewer, may not spot it. But because of my wealth of experience, and I've worked with people in South Africa, like Gideon Value is an expert in this self-similarity. We brought him for the conference in UI. He was around for the conference in UI. It's an expert. He knows it and he has been using it. So many a times when I do some work, I still refer to people that I know at the core of it. But the crucial thing is for the self-similar. If it is not self-similar, I mean, you have to go through a series of computation. I mean, the man is here and you can talk with him. I'm sure you get what I'm talking about. That will not permit me to spell everything out. But it's not difficult. But you have to work out the self-similarity. Yeah. You have to work it out. And it does not work for all equations. Like you said, this is a partial differential equation. It's different from this one. It doesn't necessarily mean that whatever I use here will work here. You have to check. But many people don't do check. They just say that because somebody did it, just put it there. And the thing will not be sensible. Okay, that's on that aspect. The second one is this issue that when we convert from partial differential equation to ordinary differential equation, we are likely to lose some information. You know, I disagree with you. See, the essence of the Longicuta is because that scheme has been tested over the years and it works perfectly. And it can only undo it in the form of ODE, systems of ODE. And that's why we are putting the ordinary differential equation, which is of order 3 in one variable, order 3, the other variable will now convert it to a system of ODE. And you realize, at least thank God you are in deal analysis, we use the function analysis solution. Anytime we want to look out for existence of solution, we do that. We try to put it as a system of ordinary differential equation in order to be able to carry out existence and uniqueness of solution. We do that. So I'm not sure we have lost any information, otherwise we need to be doing that to solve for existence and uniqueness of solution. So to me, the method is perfect and it's working, and many people are using it and will continue to use it. The third one is it's a analytical method. To me, if you have a partial differential equation and you want to solve it using semi-analytical method, it's possible. I believe it's possible. Even if I have a non-linear partial differential equation, I can attack it directly without necessarily reducing it to systems of ordinary differential equation. I can attack it directly. I have so many problems that I've met along the line. And how many people have been working on this perturbation method. The advantage of the perturbation method is to help the numerical analyst to be able to make comparison when the parameter is small. I see that this scheme is working perfectly. So I'm not too sure of the people converting first to ODE before they can now use perturbation or semi-analytical method. I'm not too familiar with them. I'm the editor-in-chief of the Journal of the Nigerian Mathematical Society for more than 20 years. And I read through the lines, I see some paper, and at times I don't want to do this projection. I want to remove the element of doubt, and then we send it to reviewers. And some of them will spot some of these things and point them out to us. And at that point, we throw the paper out of the journal. And I'm happy the journal is even being reviewed by Zenderblatt and also reviewed by Math Science Net. So we cannot push against anything. We have to be sure of the quality of the work we are pushing on. And that's why I mentioned earlier that if one of the papers are good, even with my MSc student, the citation is as high as 100 plus. And it's published locally. The Journal of the Nigerian Mathematical Society. And this was 2015. 2015, I've got more than 100 plus citation. Almost 120. So whatever you do, sure that you check your numerics very well. I always tell people that the reviewer may not be able to perform the operation. You just see what you have reported. Okay, it's okay. Make his piece or a comment and then throw it back to him. But you are responsible for whatever result that is presented. You are the one that did the work, and you have to show it. So to me, I don't. Analytical method is good, and I only support it because it helps numerics extensively. When I say numerics, numerical computation, it's used. It's very useful because you can use it for comparison. Okay, and the last one was on
Inclined plane.
yeah. On the issue of inclined plane, you know, it's like when the plane is taking off, you can see that the nose is up. It has to be inclined. Okay, so inclined plane problems are germane. They are important. And like I used to tell people, suppose I want to check the frictional force that is operating on the surface. How will I know it? It's by increasing the angle of elevation until the thing moves. Then you know that's how you. So inclined plane is very germane. That's why at the elementary school we teach them elevation, depression. You can't, when the plane is landing, it's depression. So that angle you can't throw it away. But if it's something like the sheet we are talking about that is inclined, it's physical. And so all you need is that the angle of elevation to resolve along the axis, along the x-axis and along the y-axis, as the case may be, and then continue, solving. And that's why when you look at the Boltzmann approximation for boundary layer, you will see the cosine coming into play. So that once the cosine is 0, then of course you have 1. And if the cosine is the angle is 90, then you know. So these are the issues that attraction. You can do attraction on an inclined plane. Of course, it's not the same. You have to resolve it. So these are issues that if you model properly, you can spot it. You can see it. I see review for many international journals. I have 4 on my tip now. I see the theory. And I review for them from time to time and make, we look at people on using inclined plane and they are good. Because the most example I get is when the plane is taking off and when the plane is landing. Or when you are looking at the frictional force that has on the surface, when you increase the angle slightly. These are real life problems. So it's accepted. Yeah, it's good. Thank you very much for that question.
Thank you so much, sir. I think that those questions were actually have been addressed. But before
you didn't ask me whether he's satisfied.
Okay, the satisfaction. You elders told us at a point in time that there are situations in life where you ask the child, "Have you eaten?" And thus, are you satisfied? So sometimes when we manage, we are trying to look at the time that I think I want to apply the method of the elders. All right, so Prof, now I want to play with the rest of us, both physical and online. You may still have person. Please, I believe we can still meet with their professor later. But then there's this one I cannot look away from. I think our professor has a comments that he wants to give. Really, I'll give you.
Thank you for that privilege. I mean, my intervention is just to appreciate Professor Okoya for the excellent delivery. I can see the passion that comes to it.
Yes.
Activity.
That the program is it changed?
Despite the
I should give my top of
age. Quite excited. One funny aspect which came during the presentation, we talk a lot about collaboration. And I was wondering whether outside the other bedroom collaboration,
This of 10 minutes. Yeah, I will apologize.
In your presentation, the collaboration outside the other room. Of course, I'm happy with your
Anyị ga-ebe ma anyị ga-butuje ya nye oge.
The position regarding collaboration.
Yes, no?
That Phillips, University of Ibadan, very serious people that insisting that that field is difficult to find the extent stating that there should be special promotion guideline, to favor those that feed. They can only see things like that. But I think this your position should be strengthened to change the reality. And it's also killing some of the very younger communities, making it, restricting them to a very narrow space rather than reaching out where that skill. See, mathematics is a language, and that is the bottom line. It's a language that other disciplines, statistics inclusive, physics and all of that. It's a language they have to use. That's the language we write our model. So that's the language we use to even analyze our model. So it's not something that is restrictive to a very particular area in the environment, in biology. These days you hear of computational biology, you hear of computational physics. Even in my department, when I had the opportunity of revising the postgrad, we had to create computational statistics, which I now have to implement. So I think there is need to stretch out, reach out, and I use 3 words because of us colleagues that's very this younger generation. There are 3 C's that you must learn. C, when I say C, ABC. The first C is to connect. Connect with the right people, with the right network, with the right, institution, as rightly mentioned by Prof. If you don't connect, you will not be connected. The second C is for you to collaborate. Then when you connect, the purpose is to work together. Is to partner, to work together. No one person can solve a problem to its logical conclusion. And so problems can be interdisciplinary, multidisciplinary, intra, whatever. The final C is to create something. You have to create something feasible, tangible. Thank you, Prof. You have taken a lot of investment to build.
Thank you so much for that point. That's one compliments, and I think it's well deserving. And then we all want to agree with me that our dear professor has delivered excellently, isn't it? Okay, so now, director is going to be doing 2 in 1. It's going to be making just giving a comments about Professor Koya, and then also going to be helping us to present a token, an award for this presentation that we have had today to our dear professor. So please, may I also now invite our director, so you know to.
Thank you so much, sir. First thing I would like to say that we have myself and Prof, we have some level of intersection. One is from Lagos States, So it's an attitude. And then number 2, I think I'm supposed to be in Lautech, and I was supervised by Professor Ayedi. So he was also supervised by Professor Ayedi. Myself at undergraduate, but he said I didn't already pass up to PhD level. So there is a kind of correlation. And one other thing was that Professor Koya, I've known him during my undergraduate, used to come to Lautech. I see them in the tutorial blog.
arguing on some stuff in English. So, but I began to learn more. First of all, at ICT, I was at ICT. I became with his wife, and we were discussing on this vision. You may not remember, I don't know. So, and then he said, the two of them started giving me thousands of advice. I said, wow. So the wife was saying, I should do this, that. I kept those in my mind. Said I should make sure that I have people on ground so that if I'm giving other appointed that. So all those things I kept it. And then Papa said, we will put this in notice. In this. So it was as if we are made for like 1 year, but the way they were giving me advice, suggestions, and all of that, silently I kept it. I was watching over the years. Most times we were meeting online. During we have a Christian Scientist Fellowship, you understand? So we meet online every Sunday. ICTP has a fellowship for Christians and all that. We meet when I'm there. We meet at to some Bible study. So over time, we have had to meet at one point or the other. And last year, I was invited as one of the speakers, parent speakers for their program at UI. So we have come a long way. I want to appreciate him. And the fact was also that his approach to field techniques is actually different from what I used to see in Nigeria. Yes, I must say I've told my experience of that in the Now, the approach is that it comes from the point of view of the physics of the problem. Now, most times people I read a lot of papers and then you just see somebody, you don't even know what is doing. I know this what's the best. Even the paper is from, but I can't see what he has come to do. Say I changed this one, I changed that, and then when they change it, they just send that to America. But if you look at all the papers, he will state the problem, he discuss the physics, and then because the problem is not in maths, the problem is the physics of fluid. So he tried to make us to see that which like numbers of papers in fluid Nigeria doesn't have. Which people should learn this kind of thing before. We should learn from them because a lot of people do all this kind of thing. I modify this, I modify that, and then what do you do? What was the problem? You cannot see the problem. You understand? We cannot see the motivation. We can't see the aim. So many of us talk about the method, but the method is not your method. There are existing methods that you copy from. So the question is not from the mass. The question comes from the physics of fluid, not from the mass. The mass is the tool. And that was why I was discussing the OGE, the PDEs, and all of that. He was able to state those things, which means that this is the way science should be done. You are applying your maths to solve problems in other areas. You should not just put everything together like, I don't know, maybe combustion, mathematical combustion, and then just push things and push it to people, and then people are reading. And so I've been following his work, and I see that you can read the paper and you will understand that this is the problem he's tackling. This is how you tackle the problem. This is the result that comes out. These are the conclusion. And I followed it over the years. And this morning when he was presenting, I also saw that. So let's give him a round of applause for that. I think so. They need to I don't know, maybe they need to organize, maybe in the forthcoming conference in the Abuja, you need to organize a meeting on this in terms of how do you tackle questions in the fluid mechanics for people, or how do you write a paper in fluid mechanics? Yes. How do you write a paper in fluid mechanics? So people who are doing that area, they should come and listen and follow how things are being done, so that you will not just be doing things the way it's done in Morocco, but the way it's done conventionally. Conventionally, not in Morocco, not in Shagam. Yes, conventional. So that when people look at your work, they feel like, wow, this is not just saying. So I want to appreciate him this morning and or afternoon. You are right in the afternoon. So thank you very much for coming, sir. And because Mama, please, you need to come because behind a successful, beside a successful professor, there's another successful professor. That exists.
You're not staying behind the game. I'm staying beside.
So, on behalf of International Center for Applied organized the first economic conference on advances in industrial and applied maths. Why they say I try to give you this look, thank you very much. Most people say beside, what's the change really?
That behind like okay, the source.
Yeah, it's like the source, like
Alright.
Question.
You sit up. Okay, now I will say something here. I know that some of us we are very sharp. They call NASA community. That can pass. Nice ones around. I know you got something nice. It's already at the corridor. Is that not so? Yes. Something nice is at the corridor already. All right. Well, you know something. Professor Kayin has been waiting since 1:40. He's supposed to make his presentation by 1:40. And you know we have talked.
Who is taking it?
He's an elderly person. And he's energy.
Yes.
Ready to impact. And he has been there. And you don't want to keep an elder for long. And I think it is the honor of the youth to just even go extra mile and respect our dear professor who has also sacrificed so much to stay online for us since 1:40 to this time. Prof, I want to confirm that Professor Kayin is online. Prof, are you online, sir? You can unmute yourself, sir, Professor Kayin.
It's online.
Yeah,
Please can you help me reach out to Professor Kayin?
Online.
Same here.
Online. I'm on the line. Can I start?
Prof, can you confirm you are online, sir?
Online. It's online. It's online.
Oh, great. Yeah, we would like to see your video, sir. If you can just on the video, it will be appreciated. Okay, so so Professor Kayin is going to be making his presentation now. After that presentation, we'll go for our lunch. Don't worry. And don't forget, I also told you, as there is lunch, there is dinner today. I know why there is dinner. There is dinner because of us. Right? Okay. So I would like to invite the reader of the citation of Professor Kayin so before Prof comes.
Sorry.
Mr. Samuel.
Okay. Can I start?
Citation of Professor Professor Kayin holds a PhD in mathematics with a specialization in abstract and numeric analysis. He's a full professor of mathematics, teaching and conducting research in Africa and North. He's a visiting professor at several African, American, and Brazilian universities, and a founding member of several doctoral schools. A prolific author, he has published more than 190 articles and has supervised a doctoral in 20 states in Africa and Cameroon. His current research focuses on representation theory and its extensions to certain abstract groups, such as reductive line groups, as well as non-intuitive groups. All right, can we make your plan, Professor England?
Thank you so much. Can you hear me, sir?
Okay, can I start?
Yes, I can hear you, sir.
Okay.
Please, you can start, but we can't see your video yet.
Okay. Do you see my screen?
Not yet, sir.
Do you see
So
my
we can
screen?
see your whiteboard.
Yeah.
We can see your whiteboard.
Okay, it is good. Yeah. I would like just to introduce the talk, writing something after I'll go to the Bible. Okay, I would like to thank you a lot for inviting me for this conference.
So are you sharing your slides now?
Yeah.
We can't see your slide yet. It's only see your whiteboard.
Well,
So you might need to stop sharing and share your whiteboard.
okay, let me write something. Okay.
We come.
Okay, we can see your screen now, sir.
Okay, thank you. Can I start now?
Thank you.
Okay. Look, I would like to talk about some Buckner theorem, which is a Decta Buckner theorem, which is a generation of the classical Buckner theorem. You know that in harmonic analysis, in abstract harmonic analysis, the main problem is the problem of decomposition of a representation into a irreducible representation. So I would like the Buckner theorem is a method to construct, to give some decomposition when the representation of your group is not finite dimensional and the representation is not unitary. So I will just take the screen and write something before starting the talk. Let me present. Okay, yeah, listen. Okay, when you have something, you have a group, you have like a topological group, and you have a Hilbert space like this. And the problem, as I told you that the representation, any representation of the group into a Hilbert space is not necessarily discretely decomposable. When the representation is finite dimensional and unitary, you can prove, you can have some decomposition of this kind of representation. That means that there exists when this, if you put that pi is a representation of J into H like this, your pi can be right that the direct sum of some representation like this, pi I to n like this, when pi I that is irreducible. So when n here, when your representation pi is multiplicity free, your n, which is the multiplicity of pi I into pi is equal to 1. Then you can write your representation like the direct sum like this or pi when any multiplicity of n is equal to 1. But when now your representation is not finite dimensional, so you cannot decompose this kind of representation into irreducible representation. So you use what we call the direct integral direct representation. So I would like to tap you. So I'll go back to the screen. Okay. So we suppose that we take a locally compact group, a TK, which is just a compact subgroup, which is large in J. And so data is an irreducible representation of K. K is compact, so this data is finite dimensional. We construct what we call the P data spatial Grassmannian space where P is the multiplicity of your data into the restriction of the associated representation to K, like this. So in the classical one, when you have G is R, like this, do you get me? Huh? Okay, is it okay? Hello?
Yes, it's okay.
Okay, that's that. Okay, that's one. So your Fourier transform in the case of G is R, you can rewrite like this, where E, the exponential one here, is just a character of your representation when G is R, which is also a finite dimensional in the representation, one-dimensional representation of R, which is that exponential one. When you are not in R, let us consider a G, a locally compact group, which is not necessarily R, and you pick into this group K, which is compact subgroup. You consult what you call that the space like this, the space of function, continuous function, which is bivalent by K, which is continuous. When this space is commutative, you can consult this kind of representation like this, complete it. And the exponents one is like 5 on this. So let us go to the screen to explain you more what I'm saying, please. Okay. Like this. We suppose, first of all, that I take a function like the f, which is continuous, and the positive type, like this, a function like this. So this function f of x, you can write like in the integral over r of the exponential r x like this, the mu of x. So we can associate any function which is continuous and positive type, we can associate to some measure, bounded measure on R like this, which is also here just the Fourier transform of this lambda like this, which is called this with x like this form. The exponential one is just a character of when you have the group is R, which is a one-dimensional representation. So when you have f, which is continuous and positive type, you can associate this kind of f to some representation. And you got the direct decomposition of this representation into some from character like this. The mu of x, this thing, which is that the character of it, which is one-dimensional. So any representation in R, you can decompose it like the direct sum, direct integral of characters like this. When the case, we are in the case where J is R. But when J is not R, we take G like a locally compact group, which is not necessarily R. We can put into J some subgroup, from compact subgroup in J, such that the pair obtained here is what you call it. You call it that is a Gelfand pair. That means that the algebra of continuous, which is bivalent by K, is commutative. So you can define what you call the spherical function on J into K. So let us explain it for you. So we think like G like this. I put the F, which is just continuous and positive type, and also be bivalent by K like this. Your F can be like, you can associate any F to a measure on the space of spherical function on G like this, such that your F can be right that the direct integral of some spherical function R mu of x like this, where here is spherical. Use the spherical. So if F is continuous and positive, which is also bivalent, your F can be associated with some representation pi like this, we can what I mean, admit some vector u, which is k invariant by pi and also cyclic, such that your f or s can be like that the scalar product, or in this one, the pi of f of u like this. So I mean that if I summarize what I'm saying, when you have a function which is continuous and positive type, you can associate some representation like this. So from this disintegration of f, you can obtain also the disintegration of the associate representation of f like this. So that you have, when you associate this one in your representation, you can also give the direct, when I pick f in this condition, you can associate this kind of log from u, which is also a bounded measure on your space of spherical function, which is positive type, such that this function on x can be written like this. That can be like that, the indirect integral of wx mu w, where w here is just spherical function. From here, you can have also a decomposition of the associated representation like this, which can be decomposed like the direct form of pi I like this, where pi I is irreducible. So when you have a group, you have the representation of group, which is not finite dimensional. You cannot decompose this kind of representation into a true representation. But you can also, decompose it continuously by using the direct integral to decompose this kind of representation, which is called the Bochner theorem in the general case. So today, what I'm going to talk to you, I will suppose that you have G, which is just locally compact group, and I pick also K, which is a compact group of G, such that the pair is not Gelfand pair. So we'll consider a irreducible representation delta on K, what is called an element of the dual, interdual of K like this. That means that data is finite dimensional, irreducible finite dimensional of the group K. K is this compact, donc, so the dimension of K, of any representation of K, is finite dimensional. So I will consider, when I put that PC data, that the character of the representation data, and we multiply this by the degree of the data, you can put that, is called that key data like this. But when you consider the translation of f with this kind of function, which will be equal to the, at the left also like this, it is equal to ff. That means that you have a space, the general case, which I will note that the EC data of J, which is not necessarily commutative, if data is not trivial. But if data is a trivial representation and finite dimensional, you get what to mean that the space of continuous binomial case will give you the classical case of spherical function. Here, we define what we call another spherical function, which is the extension of the classic one, which we call the spherical function of type data. We call it spherical of type data. The space of this kind of spherical function are denoted by this on J, data on J. J is locally compact group. Data is an element of the dual, the unitary dual of K, that is. So this one, you can compose it, is a locally compact space. So we can associate some measure like this. If you take any function which is continuous and K data invariant by K, you can associate this kind of function to some representation. We can call like this. So your f can be write like the direct integral also by some function, which depend on the data with your measure, which you find of data, which is you have another decomposition of any function which is not necessarily bivariant. Just the function which is just k data invariant function. You have this one. So what I'm going to show, I'll tell you. So let's start goes to the screen now and explain you more. Okay, so we are here. Okay, so I give you that's a first physical function. When you have R and 0, you have a Gelfand pair. When the classic 1, where the spherical function is just exponential 1, which you have it in when you compute the Fourier transform on R. But if you are not in R, you can get some, if you have some, for example, I'm in the Lorentz group, you can pick the subgroup which is compact in Lorentz group like this, and also a Gelfand pair. And you can compute also the spherical function constant discard the which is general second, which is not in R. So we have many spherical functions associated some group for general group which are necessary in R. Now, what you call the Grassmann spherical Grassmannian, you have a group like this K, which is a compact subgroup of this, which I suppose that the K is large like this. Data is the element of the dual, unitary dual of data. I put the data like this, something like that. And from here, I construct a space of function denoted by EC data like this, which is the general space of the space of the algebra of continuous function, which is K data invariant by your function like this, which is the intersection in between that this one is the centered one, and this one is the invariant by K, when K is just necessarily compact group of your G. So from here, we define this diagram. Key here, is that what they call the representation, the algebra of bivariant function. Here is a space of character of this algebra. From here, we compute what we call the Gelfand function, the Gelfand transformation, which is just a space from the character of your algebra, which is commutative, into C. But if you put data, an element of the dual, unitary dual of the algebra, you construct another algebra, which is the extension of this kind of algebra, that is. But when data is one-dimensional in travel, you get this kind of algebra. So this algebra is an extension of this kind of algebra. And from this algebra, you can compute also the Gelfand transformation, which lead you to the Fourier transformation, which is the extension of the classical Fourier transformation, what we call the Fourier transformation of type data. Okay, so yeah, what you want to construct the element of this kind of Fourier transformation. Fourier transformation of type data, you have to compute first of all the spherical function of type data. I'll give you an example. This theorem, which is proved five years ago, when you keep that K is a compact subgroup, which is uniformly compact subgroup of D, I suppose that this one, K here, is the centralizer of the Lie group of your compact K subgroup of D like this, and you consider the universal enveloping algebra for this. And using the fact that this representation U phi is irreducible, you can get some function phi, which will be spherical function of type data. In the way, it says the simple way to construct this kind of spherical function. From here, you can construct now the Fourier transformation when you consider when your pair is not a Gelfand pair. Okay. From here, when phi, suppose that phi is just continuous and the positive type function like this. Phi can be written like this. Exponential I lambda x is just a character, which is the finite dimensional representation, one-dimensional representation. We can associate this one is a representation. This one is just a direct disintegration of any representation into a one-dimensional representation like this, which is a character. Is when the case of D is R. But when D is not R, we compute the space, the first like this, which is the space of spherical function of type delta like this. And we can associate this kind of function, which is bivariant, continuous, and bivariant by K, to some measure, bound measure on this kind of space. When you can also decompose this kind of function into some spherical function, which can be associated for the pure representation. I mean that a pure representation is just a representation which can be associated, just a pure function, just a function which can be associated to the irreducible representation. Like it's called the pure representation. So any function phi which is continuous and bivariant by K and positive type, you can have this kind of decomposition. From here, you have also, when you consider the representation associated of this kind of function, you have also the representation into this decomposition. Okay, but the general theorem, the classical theorem, when J and K are Gelfand pair, you have this one. So when you have phi, which is continuous and bivariant by K, you have this measure on this one side that you can write like that, is what I'm just saying. Now we can consider the spherical form is also pure, is also extremal. So pure, that means that the representation associated is irreducible. So when you have phi, the representation associated to the phi, which is spherical, is pure. So the representation associated this kind of function is also irreducible. So from here, we can have this kind of decomposition. We suppose that K is a subgroup like this. K here is the unitary dual of K. That means that K contains the class of representation which is finite dimension and irreducible of this group K, the group K. When K is a compact, that means that the degree of data is finite. So you can compute the key data, the character, with a generalized character of your group. Using this character, you can compute what you call the spherical function of type data like this, Z data of G. And also associate this kind of representation with data, you can decompose this like this form, which is called the general case, a data-Bochner theorem. So, okay, let me explain it with my on the screen. Okay, what I'm saying, you have K like this, a K like this contain the class of representation of K like this. So we compute an algebra which depend on K, on D like this function, which is not commutative because D, K is not Gelfand pair, like it's not commutative. This one is not commutative. From here, we consider the spherical function, which are denoted by phi. It is a function which is bounded also, and K data invariant. That means that the phi the convolution product phi of the key data is equal to of key data from phi, where key data here, chi data is just the degree of your data with some character of this one. If this one is called to phi, you have some element of this kind of algebra. So your phi here, you can associate of this one from a representation. Something. I have some problem. Yeah. Okay, so it's good now. Okay. You associate this one is from a representation like this, which is called pi phi like this. This pi phi can be associated with some from major on the space z data of d, such that this pi phi of phi can be like the direct integral of u data of like this some function of phi d mu of phi, well, like it is called the data which is w, that w is the element of z data of d. What you call the direct, the disintegration of any representation which will not travel into some spherical function which is type data. This one is a spherical function. Phi is data is spherical function, is also pure. It is pure. The representation associated with this one is irreducible. So you can decompose any representation of your group into the direct sum of irreducible representation, which is very useful when in quantum mechanics, in company, because you associate this kind of representation with elementary particle when the work is irreducible. So this one, that's the main result you can have like this. Where here is a spherical function in the space, a spherical function of type data, depending of your data, which is just the character, the element of the dual unity of this one. You have this kind of connection for this. This one, if you associate this for this your representation, you can have, instead of writing your p pi like the direct sum like this of pi I like this, you can just here when the group is not the representation is not finite dimensional, it's just unitary. You can have this kind of direct instead of this, you have this one, which is very useful in quantum mechanics when your representation here associated with phi is irreducible. So I would like to summarize it and I stop there. So what I'm going to say, your group is the group is considered a locally compact group. When I consider that pi here is a representation of J into H. Here is a Hilbert space. Like this. When pi is a finite dimensional, that means that the degree is finite. And when pi is unitary, like this kind of representation, your pi can be right that the direct sum like this, and I or pi I when I is 1 into granted, which is necessary, we can be infinite like this. This n I here is just the multiplicity of your representation I into your representation like this. That means that the pi for all I, pi I is contained in this kind of representation like this. Is contained n I times. It's why you can decompose this kind of it. Here, in the case where your group is a finite dimensional, the representation is finite dimensional and just unitary. When the representation is not like this, when the dimension is not finite, the dimension of representation when is equal to is not finite, we can give some discrete decomposition like this. Pi, like the direct decomposition of u theta, which is depend of like this, your theta of x, d mu of u when you put that this one, or where here in the space of spherical function of Z1. What is the first one? Which is the classical one. When the graph is not pair, you can have also, when you consider data an element of here, you can also define the p data, which is the general case of this, which you can be right also by the direct decomposition of some spherical function of type data, and this one you have this file which is just a representation, the measure, bundle measure, and on this your space which is z data on this kind of function. So when you have a representation which is not finite dimensional, which is not unitary, we can get some decomposition of this kind of operation into a representation using the Bucknell theorem. What is the goal of this kind of theorem? How to decompose any representation which is not finite dimensional into a representation which is we are all irreducible. So I can stop there. If I also have some question, I can give you more detail about what I'm just saying. Thank you.
Thank you so much.
Hello?
I can hear you, sir. Thank you so much.
Okay.
Thank you so much for that presentation. Just see if you can have one person who have any question. There's just one question. Anybody? Any question? Online participants, any question?
Any question? No question.
Okay, so the answer to the question, just going to Prof. To take this remark.
Attendance for the
Thank you so much, Prof.
decent. For the
From kind, let's see your face.
Go to meeting.
Yeah, thank you very much, Prof.
Turn on the video.
I'm very grateful for coming. Thank you for your talk. Thank you for taking out your time to teach us. Appreciate that you finally were able to make it. Thank you very much. So when are you coming to Abidjan?
Maybe
anytime soon.
I will come back in April.
I can't hear you.
I'll go back to Abidjan in April. So I'm giving the course. I'm giving the course here because after the course I'll go back to Abidjan.
Okay. So I'll keep you on. Thank you very much. Let's see.
I think that I will see you at the Congress when ACOPAM, which will be arrived in June. Try to share the news in your country.
Okay. The Pan-African conference.
Yeah.
Okay. Yeah, I'll do that. Thank you so much.
Okay. Just to say something to finish that I did not give you an example. So you can, for an example, when you take like the Heisenberg group, and you give the group G like the group of automorphism of Heisenberg group, you can pick into this group a compact group which is not unitary group, which can be your K in this case. So I don't have time to develop some examples. Okay, see you.
Thank you so much. Thank you so much. Thank you. All right. I want to believe you. I think we are trying to buy 10 bites. That's why we are asking to eat like a VIP, not to go and keep your food. Let somebody bring your food for you. You sit and just eat. I think it's a good one, right? Are you enjoying your meal? It's a good one. Now, let me announce to us that we have 2 more events for the day before we go switch into another mood, right? We are seeing the mood of conference. Is that okay? And we have 2 major events left for the day. We have one of our keynote speakers who is also going to speak today. We have the last parallel session for the day. Let me confirm. Rocky, are you available already, sir?
Yes, I am available. You hear me?
So I'm very glad you have been there. Thank you so much. Now, it happened to us at this end that we had some very challenging technical issues that took our time. So that's why everything has been like that behind schedule. We want to play with you for 10 minutes so that the people have been sitting down back to back for a very long time. We just want them to stretch out 10 minutes so that they can enjoy what you are going to be discussing. We know that what we've been bringing on board is a very important aspect of this conference. And we want people to be able to catch it with all their minds able to have attention on this. So please, we're pleading with you, sir, to give us 10 minutes for people to stretch. Is that okay by you, sir?
I have a question.
Hello, sir.
You talk to me.
Okay.
Can you hear me? Can you hear me now?
Yeah, I can hear you. Yeah.
Can you hear me now, sir?
Yes, okay, I can hear you.
Okay, so what I'm saying is that we want to play for 10 minutes from you at this stage. There are some challenges that will be technical issues. And for that, people have been sitting down for long, back to back. And we just feel that what you want to discuss now is very important to this conference. I would like people to be able to concentrate, focusing on what you are doing, but they have been sitting down for long. So we want them to stretch by 10 minutes so that they can come back and then be able to focus on
Okay, great, amazing. Okay, great, thank you.
We are going to stretch now for just 10 minutes. Please just round, stretch, get some fresh air. What's time now? This 3:57. That means by 7 minutes past 4, we are all to be here seated. Thank you. And online participants, we are at this end, we are going to stretch out now and then returning 7 minutes past 4 for the last keynote speech for the day. After the keynote speech, then we will have the last parallel session for the day. So that means today is going to stretch beyond normal a bit for us. So please, let's do that. Now, 10 minutes. Let's go out. We have our 10 minutes. Ready. Thank you.
I have a question. Please.
All right, thank you so much. We are back. We have spent extra 30 minutes beyond what we requested. Again, it's the hour issue. No problem. I believe that things are getting better. We are happy to have now Dr. Rocky with us.
Yes.
Engineer Rocky, is ready. And we are going to be reading the citation of Engineer Rocky before he starts his presentation. And to do that, please, Mr.
Yeah, great. Do you see my screen?
Yeah, we can see your screen.
Okay, amazing.
We want to read your citation first before we
Yes,
take
it's
the
just
presentation.
to confirm it before starting.
Yes, we can see your screen. Thank you.
Okay.
The way you arrange everything.
Engineer Rocky Zendo. Sorry if I didn't.
Engineer now.
Therefore, SME and technical architect with 13 plus years of experience delivering scalable, excellent, and production-ready software, IA solutions and systems. Experts in Java, Spring, microservices, implement, train, and test model, API design, CI/CD pipelines, container orchestration, such as Kubernetes and Docker, and cloud infrastructure, such as AWS, OpenShift, GCP. Proven ability to lead architectural design, ensure development, reliability, and collaborate in agile environment. Experience with high availability system in finance, banking, and insurance. Thank you. That is the citation of engineer.
Yeah, thank you. Thank you, everyone. Everyone, do you hear me very well?
Yes, very well.
Yeah, great. I would like to thank first Professor Bakare for inviting me for this invitation, because I would like to we want to participate to the improvement of the technology and innovation in Africa. So I would like just to complete my profile. Who am I? I am also the chair of the Industrial Commission of ASHAM, which is the African Society for Industrial and Applied Mathematics. So on which we collaborate with Professor Bakare in this commission. So now on today, I would like to fix in some mind some concept, because we have keywords on our current day, AI, data science, machine learning, deep learning, but where is the starting? How it starts, and what the concept based on all this technology or all this concept. So why data science and machine learning matter? Exactly, it is to transform some data into actionable knowledge, to help empower modern decision-making system and enable solution to complex business problems. If you focus on machine learning and deep learning keywords, these two ways, these two keywords are based on some algorithm, where we can focus on main algorithm, decision tree, random forest, gradient boosting machine, adaptive boosting, AdaBoost, and extreme gradient boosting. So here we can see the decision tree is the basic concept, basic algorithm which is used by all other.
Nigeria.
To assess the adoption, the industrial adoption of all these tools and method and concept and role, we have Kaggle survey, which use more than 10,000 respondents, which assess which tools are readable now on are readable at the real time. So it's very important to assess at the real time which framework is the best for the current time. So you can have a look into this, and here we can see that GBM, so the gradient boost methodology, and XtraBoost the methodology, which is one of the best used now on our current day. You can see also here the GentleBoost, okay, it is the same, and AdaBoost also. It is one of the most used on our days. So it reflects the industry perspective. Let's go to some history. Since 1950, the concept of a Turing test is come up by Mr. Turing, who put an algorithm to an experimental to evaluate if a tester can push some request both to a machine or human, but they don't know and the result to avoid the tester to know which of machine or human has response. So that's the beginning of the machine learning of all this concept. And after that, we also have a perceptron in 1957, which based on the concept of we have many inputs, and depending on the depending on the weight of each input, go to how to influence an outputs also. And after we have used add some layer, a hidden layer, which influence more influence the outputs. That's the starting of artificial intelligence. Modern machine learning is used definitely in some cases like data-driven learning, GPU computing, statistical learning, and big data. We have to talk about some algorithm before. Let's take the most one, because if you remember, the most used was the GBM here. So we focus on it. Okay. The GBM is an ensemble of small decision tree. So where each tree correct error for the following tree which will be created. So that generate a strong model from a weak learner. So the previous tree is considered like a weak learner because they generate some error on which will optimize the model. We can see here an example. So the data we generate, you have a first tree which make some prediction and will influence the second one, and after this you will influence another tree, and the final prediction will be the unstable prediction will be more stronger. Yeah. So we are talking about decision tree to define gradient boost tree. What is the decision tree? A decision tree will be it is like a tree, yeah, to help us to make a decision from an input. It's a recursive split. We have the root, the notion of node, which corresponds to a decision, and leaves, which correspond to a prediction. Let's take an example with the erase data set, which describe the factor of length and width of sepal and lepal to predict if it is a setosa, a versicolor, or virginia species. You have an example here. The first root in the decision tree concept, we start with a node, with a node which is a decision. So we say all the sepal less than 6, it is the root node. It's the first one called root node, and and by the other node from the other depth except 0 are called leaf node. So let's take the scenario. Let's take the scenario to illustrate the decision tree. If we consider, if we have a sepal, we have a sepal lens, a population first. If you have a population of 150 with each species with 50. So a population here, each one is 50. 50 setosa, 50 versicolor, 50 virginica. We take the best, one of the best scenario, the condition which gets us the best scenario. And the condition is, for example, sepal length superior and equal than 6. And the second condition, if the observation has a sepal length superior or up to superior or equal to 6. If it's not, it is a setosa. If yes, we have to evaluate another condition. If the petal length is superior or equal to 5. And after we have, if yes, it's a virginica. If no, it is a versicolor. So take an example of a sepal with a length of 6. We have here, if the sepal is equal as 6, directly we have, yes, yes. If it's equal, if you have a population, let's imagine we take setosa. We have one setosa. How can I say it? Yeah. If we take the population, we have for setosa, it's classified. If you have all setosa, it's classified here. If it is a setosa, we have setosa or both virginica or versicolor into our data sets. So you can see that setosa is apart. So we have 50 setosa and 0. If it is not setosa, we have 0 virginica and 0 versicolor on this leaf, on this node. And the other nodes, we have 0 setosa and 50 and 50, virginica and versicolor. If we have one, we take an example of a repetition of our data set. We have one virginica and five versicolor. We can say that here we have one virginica and 5 versicolor. So it remains here 49 and 45 45. And from that, we can evaluate the probability for our observation, our population, to have setosa or virginica and versicolor by taking each of the end nodes. So here you have the end nodes for setosa is 54. So we have 0 to 50, 54, because we have to remain 0 by 0 by you remain 4. You have 0. You add 0. You add from your 60. If from your 50 here, you add 4, and you have all your data set. And for each one, you put the 0 here. Let's see here. Yeah, exactly. Here you have 49 plus 4 plus 5, which means 64. So for setosa, you have 0% to be a setosa if it is a virginica flower. If it's a versicolor flower, you have 49% of probability to have a versicolor, and 5% probability to have a virginica for a versicolor flower, for example. So you can do it also to evaluate the probability for a virginica flower to have a virginica flower here. So it is a concept of decision tree. The decision tree also, after that, you have, when you have how to distribute your you evaluate the probability. What you can do to introduce the concept of purity. So in this concept, the way is to say that to attain the one, to attain what is the probability, the inequation, what is the good inequation to get the best classification. And for that, you have Gini index, which will correspond to the purity, where you remove from one the sum of all the probability we had before. So we have here one less, if we take this one, the first node, we have 1 minus 50 for each one, divided by the total 150 squared. And you do it, you calculate the Gini index, and you have a Gini index for each node, which give a power of each node, which give a weight of each node, definitely. And here you can see that here we have a good, the best Gini index is this one. If you continue, this Gini index is just to calculate, help us to calculate the node cost. It's just a tools to calculate a node cost. And this node cost, we will be going to calculate it by splitting minimize impurity. So we have to compute the engineer index and to minimize the impurity. And for that, the cost, you have to evaluate the cost. For this cost, we have to evaluate the cost on the left and the cost on the right, and you make the addition. So here the cost is 0 because we have a Gini of 0. The cost, the 0 multiplied by the number of not versicolor, the number of setosa, divided by the max, divided by the total. So here we have a left cost as 0, and the right cost, if you make the same calculation, we have 0.5, and half. So, and you make, in addition, we have the node cost for this one is 0.33. So in the concept of decision tree, we make an evaluation of each node, and this evaluation pass by a Gini index to evaluate to remove all the impurity and calculate the cost of each node. That's what I have presented. And you, after that, you can have this separation, which show you here we have 1, 2, 3, 4, 5 Virginica into the versicolor, and you can illustrate it is illustrated by this graph. You can see like this, and this one we have 50 and no versicolor or Virginica. Let's go to another concept, which is a foundation of the gradient boost, tree. It is the Adaboost tree, because gradient boost tree is based on Adaboost tree algorithm. In this concept, we have yes.
Thank you, sir.
I don't get you.
You have 5 more minutes.
I don't get you very well.
You have 5 more minutes. 5
more minutes. Okay. We're going to very quickly. So, Adaboost is an algorithm which will generate, if we will base on the first tree, and get the feedback from this tree, which will influence the data, the training sets, and so on and so on and so on to optimize the model. So the tree, the Adaboost as a concept is very good concept where we have a weak depth, because we have just, it is a stump with a leaf, but with just one depth, not more. And this depth and this tree influence the other, influence all the model. Let's go further. You can see here, you have a training test here, a training data set here. You have a model which gets an error, where we can have a total error, which will introduce to the all data set, and this new data set will be generate another model and generate another error, which be introduced to the new data set, training data set, and so on and so on. if we have an example here, we have Titanic, for example, a Titanic passenger, which we describe who survive depending on some factors, sex, age, classes. We associate a weight of 1 to 5 of each observation for the first 3, which is the same, because for the first at the initiation we have the same weight. So let's imagine it is the sex variable which give the best results. So here you can see all the men are considered as non-survivor and woman survivor. If you make, because here 2 is a woman, is considered like a survivor in our data set. So we will going to calculate the total error. If you remember, I was talking about error, this one. We can calculate it by make the sum of, if we have this function, this means that it will a vector of 1 for each incorrectly predicted observation, and 0 for each correctly predict observation. So if it is correctly predict, is 1, it is 0. If it's incorrect, it's 1. And after that, integrate the total here into the to calculate the proportion of that tree. So here it is the proportion of that tree which will influence the model. When you calculate it, it makes, for example, for the incorrect predictable 0.4 here, it is influence the incorrect predictable, yeah, and for other, we calculate for other, it's make 0.1 for the good predictable, and after that we make a normalization to have 1, because the sum of this is 0.8, which is not, we have to have a sum of 1. So we normalize it, and we can recite the process as with many to have many trees as we want. And when we have trees, we can see here, if we not consider the weight, we can see that we have more, how to say, 1, 2, 3, 4, which were women, how to say, men will survive, or we have most, how to say, 2, 4, and 6 with the highest weight, where we see that the woman will not survive. The men will not survive, and the men with class 3 will not survive. That's the concept of AdaBoost. And from that, if you come back to gradient boost formulation, we have a sum of decision tree where we will outate. Which work incrementally and whose model combine result along the way. If you have here, the difference between AdaBoost and gradient boosting is, first, we don't start with a stem. We start with a leaf, which corresponds to the mean of our population, of our observation. If we take an example, and also that we have also the weak tree, but the other tree is not a stump, only the stump, but we can have, even if it's a weak tree, it is not only a stump with a one death. if we take an example also, we want to predict a house depending on some factors like years of construction, area, number of room. The first leaf will be with the price average. The residue, the current price, which is the current price minus mean price, which is the first value of the optimized value. The optimized value is this one. Let's take the most valuable criteria. Taking house, which area up to 80, and has more than 3 rooms, or if else it predict 60 here. Another criteria is if the number of room it's up than 3, up to 3, predict 10, else minus 60. Add the prediction of this 3 residue, which update the optimized value here, which is the mean to reality, which is near to the reality. We can also integrate a factor like called learning rate between 0 and 1. We will show the contribution of each tree to the model. And this is optimization factors, definitely. The LL, the learn rate. And after that, we will have the prediction to be the final. You have the sum. You have to make the sum of all the prediction to have the final optimized rate here. All the prediction, you have to make the sum of all trees prediction to have it. And definitely the algorithm we have, yeah, it is the last one. It's the last one. Yes. So and we have here the algorithm where we find the cost. We analyze the tree first. The cost function. We initialize the tree with the mean. We calculate the residue here, which train a tree of with data, and update this tree by adding by make the sum from the first one, the mean, and all the training factor constituted by the residue and the data. And from that, we can say that even if the limit of the gradient or decision tree and all the trees is that it's human interpretable, but when we have more data, an abundance of data, we cannot use it. And it's the reason for why we go into efficient optimization algorithm like a neural network, which is the following of the machine learning and deep learning. Thank you. Thank you for your attention.
We thank you so much, sir. Thank you so much.
Yes.
We are so honored to have you present this fantastic concept. Thank you so much for the presentation. So we just have chance for one question. Anybody have a question? Or anybody? Just one question.
Either physical or online.
Either physical or online. For question participant, do you have any question? Any question?
Any question? You have eaten a lot.
Okay, we have the question. Okay, Mr. Oh. Okay, yeah.
I don't understand.
Presentation doesn't mean admin has removed the person.
Yes, he has been sleeping.
Yeah, I cannot hear because there are some noise, please. Yes.
Also take you see I'm thinking.
Hope you can hear me now.
Yeah, I can hear you, but very, very low.
So I want to know the reason behind decision tree. What is the motivation? I may say I have an idea of what it is, but what is the motivation? Why must we use it? And to what, when you at some point you explain why we transition to machine learning, I think towards the end of the presentation. But to what complexity, to what level of complexity do we transition from, the tree or the trees? Because there are different type of trees that you mentioned.
Yes.
So to what level of complexity do we transition from, decision tree to machine learning?
Yeah, definitely. Thank you for your question. The transition, as I said before, is the number of layers we can put, that's the first point, the number of layers we can put to interact each other. Because on the tree models, you have, it's only one sense, top to bottom. And a leaf, which is correspond to a node, at only one or many two, generally two leaf. So it is limited. In the near model, like image recognition, for example, we have to have another type of experiment algorithm where we can have a node with many type of with many dependency, and this node will be, and the interaction will be in the two sense, for example, definitely, because on the tree we don't have one sense. So I don't know, we have to go deeper, but that's the basic way. The abundance of data and the model, the model which not corresponds to the decision tree, definitely is what I would present. I want to present that the limit of the decision tree based on it is just one node with two leaves, yes or not, and going on one sense, where neural network we should have for one node many connection, and on many sense, that the complexity we have to pass to machine learning. I don't know if I have this answer to your question.
Yes, the question is answered. Thank you so much. So we're just going to take Maxwell first.
Oh, thank you, Rocky. Very, very grateful. Thank you for coming. Thank you so much. I really appreciate you. So Rocky is part of an industrial partner in the African Society for Industrial and Applied Mathematics, where I preside over the West African region. So he has been working with us from France, and I want to appreciate you for your efforts and for your passion. He has been waiting since 1:48 p.m. and did not go. So can you give him a round of applause?
Thank you.
So we appreciate you. So have a nice evening. God bless you.
I promise it's a debt, so I promise it, and I am here to be. Yeah, it's a pleasure. Thank you, everyone.
Well, I thank you so much. We are very happy. Okay, so the last session for the day is going to be with us here, the people
the participants, physical and online, with our presentations.